All right, welcome to part 3. Now we're going to look at example 7. Use the Maclaurin series in the table to obtain a Maclaurin series for the given function f of x equals the square root of 1 plus x. Well, we don't have anything that looks like that, so I'm going to convert this to a binomial, 1 plus x to the 1/2 power, and now that matches my binomial raised to the k power. So my k is going to be 1/2 when I substitute this in. So 1 plus x to the 1/2 power equals the summation n equals 0 to infinity of 1/2 and x to the n. So this is where we're going to build these k values. So this is 1 plus k 1/2 times x. All right, next 1/2 times 1/2 minus a 1 over 2 factorial. So if we simplify that, this now becomes 1/2 times a negative 1/2, or a minus 1 over 2 squared with x squared on the top over 2 factorial. My next term will be 1/2, and again, the next term k minus 1, so 1 minus a half, there's my negative 1/2, it's going to be there. Now it's 1/2 minus 2, which is negative 3/2, over 3 factorial times x to the third. So 2 negatives is going to make this a positive, so it appears we have alternating signs. 1 times 1 times 3, that's the 3 times the x cubed. Now it's 2 to the third over 3 factorial. So I see the pattern here. The next one will be minus 5/2. So that's going to now be minus 3 times 5, x to the fourth, over 2 to the fourth, because I'll have 4 denominators of 2 times 4 factorial. My next term plus, it'll be 1/2 times negative 1/2 times negative 3/2 times negative 5/2 times 7, negative 7/2. So 3 times 5 times 7, x to the fifth, over 2 to the fifth, 5 factorial. Minus, then we put a times 9, x to the sixth, 2 to the sixth, 6 factorial. So I see the pattern here. So again, this is when n is equal to 0, n is equal to 1, n is equal to 2, 3, 4, 5, and 6. So this is where I see a distinct pattern. So right now, these two terms I'm going to leave alone unless I can get them to fit into my pattern. But then this is going to be plus, negative 1 to the n minus 1 power, starting with a 2 for my n. 2 minus 1, we want to get that negative, so that's a lock. Then x to the n power, because the power on all my x's match up with my n. All right, and then I'm going to have this 1 times the 3. Now there's a 1 that I could put here. That's from this one. That 1 can be here, here, here. So in red, the 1, 3, 5, 7, 9, 11, so on and so on and so forth, out to 2n minus 3. So again, remember, this is when n was 6, and we needed a 9. So 2 times 6 is 12 minus 3 gives me the 9. Or when n is equal to 5, I need a 7. 2 times 5 is 10 minus 3, that's my 7. On the bottom, it's our 2 to the second, third, fourth, so that represents 2 to the n. And then 2 factorial, 3 factorial, that's the n factorial. Okay, so we got to do something with what's in red here. First two terms are the same, and everything here in red is going to simplify to the following. Negative 1, or I should say in red, 2 to the n minus 3 factorial over 2 to the n minus 2 times n minus 2 factorial. I know what you're thinking. Where in the world did I pull that out of thin air from? I'm going to show you. It's just that I don't have enough room on this slide. So I'll show you where this comes from. this is a factorial to me. The only problem is there's no even numbers, and that's what we're going to divide out at the bottom. So let me take this to this new slide. Now I have room to work this out. So again, when n is equal to 2, n is equal to 3, 4, 5, and 6, I'll show you how this all worked out. When n is 2 on the top, I needed a 1 factorial for this one right here. So 2 times 2 is 4 minus 3. That's my 1 factorial. On the bottom, if this is a 2, that's 2 to the 0 power. This is 0 factorial, 2 minus 2. So if you want, we could put that on the bottom, but that's my 1. So that's this one right here. Now, when n is equal to 3, technically on the top, 3 times 2 is 6 minus 3. That's 3 factorial. But again, I don't want this 2. So this is where the 2 to the n minus 2 comes in, because now when n is 3, we'll have a 1 down there. And I'll put in my denominators in a second, but I want to see where, trust me, the evens will cancel. So just working the numerator, as I said, I saw this as a factorial, so I wrote this out thinking this is my factorial. So 4 times 2 is 8, minus 3, 5 factorial. 5 times 2 is 10, minus 3, 7 factorial. 2 times 6, 12, minus 3, 9 factorial. So again, as I said, we want to divide out this 2. I want to divide out the 4 and the 2. I want to divide out the 6, the 4, and the 2. I need to get only odd numbers being multiplied together. So divide out the 8, 6, 4, and 2. Now, this is where I got sneaky. Now I got to find a pattern down here. Well, it's starting to again look like a factorial, but this time with even numbers. So this 2 technically is 2 times 1. And then I broke down this 4 to 2 times 2 in red times 2 times 1 for this 2. Next, I'm going to break down 6, 4, and 2. So 6 has a factor of 2. There's a 3. 4 has a factor of 2. There's the 2. And this 2 has a factor of 2. There's the 1. So I'm factoring out a 2 from every even number in my denominator. So again, here, 4 is 2 times this 2. This 2 is a red 2 times the 1. I think I may have said that backwards with my arrows when I was pointing to it. But we're factoring a 2 out of each term. 8, 6, 4, 2, factor a 2 out of every one. And then you're left with 2 times 4 is 8, 2 times 3 is 6, 2 times 2 is 4, 2 times 1, 2. Why does this make this important? It's because now these black numbers are a factorial. And the red numbers are going to be 2 to some power. So for example here, n is 6. All right, I need a 4 factorial, 2 less than 6. So this would be n minus 2 factorial. And this is 2 to the 4th. Okay, 4, I'll go n, 6 minus 2 gets me to the 4. So coming here, this is a 3 factorial, 2 to the 3rd. This is a 2 factorial, 2 squared. 2 to the 1st, 1 factorial. So again, notice that all the n values with the power and the factorial are 2 less than n, which that's where the 2 to the n minus 2 times n minus 2 factorial comes from. And oh yeah, it works over here as well. 2 to the 0 is 1. 0 factorial, 1. 2 minus 2 gives me the zeros. So that's how you simplify this sequence of odd numbers as a factorial into regular factorials, but you got to divide out the even numbers, and that's how it's done. All right, example 8, use the Maclaurin series in the table to obtain a Maclaurin series for the given function and write out the first 5 terms. F of x equals e to the negative 3x. Well, we know e to the x is the summation n equals 0 to infinity of x to the n over n factorial. So again, negative 3x goes in and replaces the x, so negative 3x to the nth power. Factor out the negative. Come on, mouse. All right, so there is my Maclaurin series. So we got to put out 5 terms. So n is 0, negative 1 to the 0, 1, 3 to the 0, 1, 0 factorial, 1, x to the 0, 1. That's this 1. Put in a 1. Negative 1 to the first, negative 3 to the first, 3, x to the first, x, 1 factorial, 1, don't need the denominator. Alternating series plus 3 squared, x squared, 2 factorial. Okay, I can see the pattern. Minus 3 to the third, x to the third, 3 factorial. Plus 3 to the fourth, x to the fourth, 4 factorial. Minus, but there's my first 5 terms. So if we simplify it, 1 minus 3x, 3 squared 9, x squared over 2. Minus 3 to the third, 27, x cubed over 3 times 2 is 6. Well, technically we can cancel a 3 here. That makes it 9 over 2, x cubed, plus 3 to the fourth, 4 factorial. We can reduce the 3, giving me a 27, and 4 times 2 is 8, and there's the first 5 terms. All right, last example here for 910. Finding the Taylor series for sine of x with a center at a equals pi over 2. Here's my Taylor series formula. We got to do our derivatives again. So put in pi over 2 for a. That's what we're going to have into our derivative. So next we'll start finding derivatives. When n is 0, it's our plain sine of x function. Sine of 0 is 1. Check that, excuse me. Sine of pi over 2. I was thinking Maclaurin series here for a second. So sine of pi over 2 is 1. When n is 1, we need the derivative of sine of x, which is cosine of x. Cosine of pi over 2, 0. Second derivative, taking the derivative of cosine of x is negative sine of x. Okay, well we did sine of pi over 2 is 1. The negative just makes it a negative 1. So I think we're going to get this alternating signs again with zeros. With 3, the derivative of sine is cosine. So negative cosine of x, we did cosine of pi over 2, which is 0, another 0. When we're 4, the derivative of negative cosine of x is a negative negative sine of x. We're back to the beginning, back to a 1. So if we start building our terms, f of pi over 2 over 0 factorial x minus pi over 2 is 0. That's going to be f of just pi over 2. All those become 1, so that's just going to be a 1 right here for f of pi over 2. Then our first derivative of pi over 2, x minus pi over 2 to the first power, 1 factorial. Second derivative, just looking at these values, increase our power, increase our factorial. So this is a 1, this is a 0, that term's a 0, so everything else is going to be 0, plus negative 1 times x minus pi over 2 squared over 2 factorial. All the odd derivatives are going to be a 0, plus the fourth, that's a 1, times x minus pi over 2 to the fourth over 4 factorial, that's a plus. Fifth term would be a 0. To the sixth, be a minus 1, x minus pi over 2 to the sixth over 6 factorial, and that pattern would continue. So if we get rid of the zeros, and now we treat this as n equals 0, n equals 1, n equals 2, n equals 3, my new summation will be negative 1. We want a positive 1, so negative 1 to the nth, x minus pi over 2 to the power of 2, so that's going to be 2 times n, so that's 2n. That works for my other powers and my factorials. So there is my Taylor series for sine of x, centered at pi over 2. And that wraps up 9.10.